The story of modern British naval aviation is fundamentally a story of agonizing compromises, a relentless battle waged not just on the high seas, but in the austere corridors of the Treasury. For decades, following the end of the Second World War, the Royal Navy found itself locked in a vicious cycle of ambitious strategic requirements, colliding head-on with brutal peacetime budget cuts. The cancellation of the massive CV-A-01 fleet carrier project in the 1960s left the British fleet relying on the significantly smaller Invincible-class light carriers through the 1980s and 1990s, while these smaller ships, equipped with the iconic Sea Harrier, proved their mettle during the desperate, freezing conflicts of the Falklands War. They were ultimately a stopgap measure, highly constrained in sortie generation, airborne early warning, and sheer offensive strike capability. By the time the 1998 Strategic Defense Review was published, the Ministry of Defense had recognized an uncomfortable truth. If the United Kingdom wanted to remain a global military player capable of independent power projection, it needed a true supercarrier. The resulting carrier strike project promised a vessel of unprecedented scale for the Royal Navy, but the naval architects were handed a seemingly impossible contradiction. They had to deliver a strike platform capable of rivaling the operational impact of American nuclear-powered Leviathans, but they had to do it on a fraction of a United States Navy budget, with a fraction of the crew, and without the immense logistical footprint of nuclear propulsion. This central conflict between towering strategic ambition and crippling financial reality forced British engineers to completely rethink what an aircraft carrier could be, stripping away decades of entrenched design dogma. They could not simply build a smaller copy of the United States ship Nimitz, designated CVN-68, because the American approach relies on brute force, limitless nuclear steam, and massive manpower. Instead, the British had to outthink what they could not outspend, leading to the creation of Her Majesty's ship, Queen Elizabeth, and her sister ship, the Prince of Wales. The result is a 65,000-ton behemoth that challenges almost every established rule of modern carrier architecture, presenting a silhouette that is instantly recognizable and often deeply misunderstood by casual observers. From its bizarre twin towering islands to its vast, seemingly empty flight deck devoid of catapult tracks, the ship looks like a science fiction concept rather than a traditional warship. Yet, every single radical departure from the traditional American flat-top design was born from a ruthless, highly intelligent optimization of resources, crew efficiency, and modern aerospace technology. If detailed technical breakdowns of military history and British combat engineering interest you, subscribe. I have got more of these coming. To truly understand why the Queen Elizabeth looks so radically different from its American counterparts, one must first look deep into its bowels, specifically at the highly controversial choices made regarding propulsion. The United States Navy has long relied on nuclear reactors for its supercarriers, providing effectively unlimited range and massive amounts of steam to power aircraft catapults and domestic ship systems. However, the British Ministry of Defense rejected nuclear power early in the design phase for several highly practical reasons. First, a nuclear reactor requires a massive initial capital investment, astronomical midlife refueling costs, and incredibly specialized, expensive disposal procedures at the end of the ship's life. Second, nuclear carriers require heavily fortified, specialized dockyard infrastructure, which the United Kingdom only possesses at Her Majesty's naval base Clyde for submarines, while the carriers were slated to be based at Portsmouth. Finally, operating nuclear reactors requires a massive contingent of highly trained nuclear engineers, a resource the Royal Navy simply did not possess in sufficient numbers to staff 2 massive surface ships alongside its submarine fleet. Instead of splitting atoms, the British architects opted for integrated full electric propulsion, creating what is essentially a floating, heavily armored power station. The heart of the system consists of 2 massive Rolls-Royce MT-30 gas turbine engines derived directly from the Trent 800 engines used on the Boeing 777 airliner, supplemented by 4 Wärtsilä diesel generators. Unlike older conventional ships where the engines are directly connected to the propeller shafts via massive, heavy reduction gears, the gas turbines and diesels on the Queen Elizabeth simply generate electricity. This high-voltage electrical grid, generating over 109 megawatts of power, is then distributed throughout the ship to power everything from the radar suites and the galley ovens to the massive advanced induction motors that actually turn the twin propeller shafts. This electric drive system provides incredible flexibility, allowing the ship to cruise efficiently on just its diesel generators to save fuel, or spool up the massive gas turbines when sprinting into the wind for flight operations. However, solving the propulsion problem with massive gas turbines immediately introduced a catastrophic architectural challenge that would define the entire shape of the vessel. Gas turbine engines require absolutely gargantuan amounts of fresh air to operate efficiently, and they subsequently exhaust terrifying volumes of incredibly hot, toxic gases. On a massive scale like the Queen Elizabeth, the air intake and exhaust trunking required for the MT-30 turbines is roughly the size of a small office building. If the engineers had followed traditional carrier design and grouped all the engines deep in the center of the hull, the intake and exhaust pipes would have had to travel straight up through the center of the ship. This single, massive trunking would have blown a gigantic hole through the hangar deck and the flight deck above it, destroying the internal storage space and forcing the construction of an obnoxiously long, single superstructure island that would severely restrict the movement of aircraft on the roof. The American Nimitz-class avoids this primarily because nuclear reactors do not require giant air intakes or massive exhaust funnels, allowing their single island to remain relatively compact. The British engineers, facing the grim reality of their massive exhaust pipes, realized that trying to cram all this ducting into one central island was ruining the efficiency of the ship. Their solution was a stroke of absolute architectural genius that broke a century of carrier design tradition. They separated the gas turbines, placing one far forward in the hull and one far aft, and gave each engine its own dedicated superstructure on the flight deck. This birthed the iconic dual-island design that defines the Queen Elizabeth class. By splitting the exhaust trunking into two separate, much smaller footprints, the engineers recovered a massive amount of incredibly valuable real estate on the hangar deck below, allowing for highly efficient storage and movement of airframes. But the advantages of the dual island extend far beyond mere internal plumbing, touching on the complex aerodynamics of flight operations and the vital survivability of the ship in combat. A traditional massive single island acts like a solid brick wall against the ambient wind, creating a violent, chaotic vortex of turbulent air right over the critical landing area at the rear of the flight deck, a phenomenon that has terrified naval aviators for decades. The twin islands act as aerodynamic flow straighteners. The gap between them allows the wind to wash smoothly across the deck, significantly reducing the dangerous turbulence for approaching pilots attempting to land vertically in rough seas. Furthermore, this physical separation allowed for a highly logical division of labor regarding the command and control of the immense vessel. The forward island is entirely dedicated to the nautical operation of the ship, housing the bridge, the captain's quarters, and the primary navigation suites, situated perfectly to give the helmsman an unobstructed view of the bow and the horizon. The aft island, located precisely where the action happens, houses the Flying Control Center, affectionately known as FLYCO. From this glass-enclosed, elevated position, the air boss has a perfect, commanding view of the aircraft approach path, the landing spots, and the complex ballet of tractors and personnel maneuvering on the 4.5-acre flight deck. In a traditional single-island carrier, these two vitally important command centers are cramped together, often forcing compromises in visibility for either the ship's navigator or the air boss. The British solution gives both commanders their ideal vantage point without stepping on each other's toes, smoothing out the incredibly stressful rhythm of modern carrier operations. From a strict combat survivability standpoint, the dual-island architecture also provides a level of critical redundancy that a single-island ship simply cannot match, because the two islands are physically separated and run off their own dedicated sensor and power loops. A catastrophic missile strike that vaporizes the forward island does not completely blind or cripple the ship. The aft island is equipped with secondary ship control systems, allowing the surviving crew to steer the vessel, manage damage control, and even continue limited flight operations if the primary bridge is destroyed. In a modern naval engagement where advanced anti-ship cruise missiles like the Russian P-800 Onyx or Chinese hypersonic glide vehicles can close the distance in seconds, this ability to absorb a devastating blow to the command structure and keep fighting is not just a luxury, it is a vital tactical necessity. The separation of critical nodes reflects a deep understanding of modern threat environments, where the sheer volume of incoming fire might inevitably overwhelm point defenses, making internal redundancy the ultimate lifesaver. But all of this physical architecture, the electric drives, and the twin towers exist solely to serve one primary master, and that is the strike fighter the vessel was designed to carry into battle. This brings us to the second massive controversy that defined the Queen Elizabeth: the total absence of catapults and arresting wires, known in naval parlance as a catapult-assisted takeoff, but arrested recovery, or catabar, configuration. Instead, the British committed to a short takeoff and vertical landing, or STOVL configuration, relying heavily on the distinctive ski jump ramp at the bow and the incredibly complex F-35B Lightning II stealth fighter. This decision was not made lightly, and in fact, it caused a massive political scandal during the infamous 2010 Strategic Defense and Security Review. Panicked by the rising costs of the F-35B and desiring interoperability with the French Navy and the United States Navy's heavier carrier aircraft, the British government abruptly ordered the design to be modified back to a catabar layout to accommodate the catapult-launched F-35C variant. However, the brutal reality of naval engineering and treasury constraints quickly crushed this ambition. Integrating the American Electromagnetic Aircraft Launch System, known as EMALS, onto a ship that was already deeply in the construction phase proved to be a financial and engineering nightmare. The estimated cost to redesign the internal power grid, strengthen the flight deck, and install the massive catapult machinery ballooned to over £2 billion, a price tag the Ministry of Defense simply could not swallow. Furthermore, operating catapults and arresting gear requires hundreds of additional specialized sailors, maintenance technicians, and incredibly dangerous deck operations, which directly contradicted the Royal Navy's mandate to operate the ship with a severely reduced crew. Humiliated but bowed by financial reality, the government reversed its decision 2 years later, permanently locking the Queen Elizabeth into the STOVL configuration. While critics immediately howled that this made the ship a second-rate carrier compared to the mighty Nimitz, they fundamentally misunderstood the staggering capabilities of the specific aircraft Britain had chosen to operate. The F-35B Lightning II is not a compromised, underperforming jump jet like the early generations of the Harrier. It is a fifth-generation, supersonic, stealth strike fighter equipped with what is arguably the most advanced sensor fusion suite ever mounted in a combat aircraft. When launching from the Queen Elizabeth, the pilot does not rely on a bone-crushing steam catapult. Instead, they throttle up the massive Pratt & Whitney F135 turbofan engine, which produces over 40,000 pounds of thrust, and accelerate down the deck toward the 12.5-degree ski jump ramp. As the aircraft hits the ramp, it is thrown upwards in a ballistic arc, translating forward momentum into vertical lift. This purely physical, elegantly simple piece of shaped steel allows the aircraft to launch with a significantly heavier payload of fuel and precision-guided munitions than it could if it were launching off a flat deck. The ski jump has no moving parts to brake, requires zero steam or electrical power, and needs no maintenance crew, perfectly aligning with the British philosophy of maximum capability for minimum logistical cost. Returning to the ship, however, presents a different set of intense operational challenges, because vertical landing is historically brutal on aircraft payload limits. In a traditional hover landing, an aircraft must be light enough for its engine thrust to overcome its total weight, which often means an expensive strike fighter returning from an aborted mission might have to jettison millions of dollars worth of unexpended smart bombs into the ocean just to safely land on the deck. To circumvent this incredibly wasteful practice, British engineers and test pilots pioneered a totally new maneuver exclusively for the Queen Elizabeth class, known as the Shipborne Rolling Vertical Landing, or SRVL. Instead of coming to a dead hover alongside the ship and sliding over, the F-35B approaches the carrier from the rear at roughly 75 kilometers per hour, utilizing the lift generated by its wings, in addition to the downward thrust of its engine. The aircraft touches down gently on the deck and uses its carbon disc brakes to stop within 100 meters, completely eliminating the need for complex, heavy arresting wires, while allowing the fighter to return with roughly 2,000 kilograms of additional weapons or fuel. This brings up a fascinating point about operational survival. Knowing what you now know about its real-world survivability and the intense compromises made to keep the budget under control, would you still want to be stationed in this machine during a combat deployment against a peer adversary? Share your thoughts below. The philosophy of extreme efficiency extends deeply into the bowels of the ship, particularly in how it handles the immensely dangerous task of moving high explosive ordnance from the deep magazines up to the flight deck. On an American Nimitz-class, moving bombs requires a massive, coordinated ballet of hundreds of sailors manhandling heavy iron bombs onto carts, riding massive elevators, and dragging them across slippery decks. The Queen Elizabeth fundamentally rejected this manpower-heavy approach, replacing it with the highly mechanized weapon handling system, a fully automated, track-based robotic network that looks like something out of an advanced logistics warehouse. Deep inside the armored magazines, automated electric moles slide along overhead rails, picking up pallets of paveway laser-guided bombs or Meteor air-to-air missiles, and delivering them to specialized, heavily armored blast elevators. These elevators rush the munitions directly into the aircraft preparation areas in the hangar or straight up to the flight deck, all controlled by a handful of technicians in a central control room. This single system eliminated the need for over 300 ordnance-handling sailors, vastly reducing the risk of human error, fatigue, or catastrophic accidents during high-tempo combat operations. This aggressive push for automation across every single deck and department resulted in a staggering reduction in crew size. The core ship's company of the Queen Elizabeth is roughly 700 personnel, even when the entire air wing is embarked, along with Royal Marine Commandos and Strike Group staff. The total complement rarely exceeds 1,600 souls. Contrast this directly with the United States ship Nimitz, which requires roughly 3,000 sailors just to operate the ship, and an additional 2,000 aviation personnel to run the air wing, bringing the total floating population to nearly 5,000 people. The strategic and logistical implications of this difference are absolutely massive. The British carrier requires dramatically less food, less fresh water generation, less waste management, and less administrative overhead, meaning the ship can stay on station longer between resupply visits. Furthermore, because there are so few people aboard a ship that is almost 300 meters long, the living conditions for the crew are exponentially better than anything previously seen in the Royal Navy, with junior sailors living in spacious, six-berth cabins with ensuite bathrooms, a far cry from the claustrophobic, agonizingly cramped mess decks of the Falklands-era vessels. However, all these theoretical efficiencies and highly sanitized design specifications inevitably crashed into the ugly, muddy reality of real-world naval operations. As soon as the Queen Elizabeth and the Prince of Wales entered the water, they were plagued by a series of highly embarrassing and incredibly frustrating mechanical failures that sent the British tabloid press into a frenzy. There were significant issues with the massive propeller shaft seals, resulting in hundreds of liters of seawater pouring into the lower engineering compartments. There were catastrophic electrical blackouts during early sea trials, leaving the massive ship drifting without power in the dark. Perhaps most notoriously, the Prince of Wales suffered a catastrophic failure of a starboard propeller shaft coupling just as it was departing for a highly publicized deployment to the United States, forcing the multi-billion-pound warship to limp back to a dry dock for months of humiliating repairs. These incidents perfectly illustrate the painful price of pushing the absolute bleeding edge of electric propulsion and automated engineering on a constrained budget. When you have no massive nuclear steam plant to fall back on, and your entire ship relies on a highly complex, interconnected digital power grid. A single point of failure in a copper cable or poorly machined steel coupling can bring the entire Leviathan to a grinding, embarrassing halt. Even when the mechanical gremlins were ironed out, the operational reality of deploying the carrier strike group revealed the severe hollowing out of the wider British Armed Forces. A supercarrier does not operate in a vacuum. It requires a massive defensive ring of escorts to survive. The Queen Elizabeth relies entirely on the Type 45 destroyer, armed with the formidable Sea Viper missile system to provide long-range air defense, and the aging Type 23 frigate to provide critical anti-submarine warfare screens. However, decades of defense cuts meant the Royal Navy barely possessed enough of these incredibly expensive escort ships to protect the carrier without critically stripping other vital global commitments. During the highly publicized Carrier Strike Group 21 deployment to the Pacific Ocean, the Royal Navy had to rely heavily on a United States Navy destroyer and a Dutch frigate to flesh out the defensive screen. Furthermore, the British military had not procured enough F-35B fighters to fully stock the massive flight deck, leading to the extraordinary situation where a full squadron of United States Marine Corps jets deployed aboard the British ship, just to ensure the carrier had a credible strike package. These joint operations, while politically spun as a triumph of Allied interoperability, highlighted the uncomfortable strategic reality that the United Kingdom had built a vessel so massive and so capable that it struggled to actually afford the aircraft and the escort ships required to operate it independently at full capacity. This is the ultimate paradox of the Queen Elizabeth class. From a pure engineering and architectural standpoint, it is a masterstroke of design. Its advanced long-range radar, the massive S1850M, combined with the Type 997 Artisan three-dimensional radar, can track thousands of targets in highly cluttered littoral environments, feeding directly into an automated combat system that requires a fraction of the traditional radar operators. Its hangar deck is cavernous, capable of housing 20 F-35B fighters and a diverse fleet of Merlin anti-submarine and airborne early warning helicopters, all movable via two massive deck edge elevators that can lift two fully loaded strike fighters from the hangar to the roof in under 60 seconds. The ship is a marvel of spatial efficiency and tactical flexibility. When directly compared to the newest American supercarrier, the United States ship Gerald R. Ford, designated CVN-78, the British approach looks decidedly smarter for a middleweight superpower. The Ford class relies on highly experimental, incredibly expensive technologies like electromagnetic catapults and advanced arresting gear, systems that have cost the American taxpayer billions in cost overruns and years of delayed deployments due to catastrophic software and hardware failures. The Ford is designed to generate up to 160 aircraft sorties a day in high-intensity combat, a staggering number that requires a massive, exhausted crew and an infinite supply of nuclear steam. The Queen Elizabeth, by contrast, is designed to generate a maximum of roughly 72 sorties a day, utilizing the simplicity of the ski jump and the vertical landing capabilities of the aircraft. For the United States, fighting global multi-theater wars, the Ford's brute force is necessary. But for the United Kingdom, attempting to project meaningful, terrifying stealth strike capability without bankrupting the state, the British solution is arguably a far more elegant, pragmatic piece of defense engineering. The legacy of the Queen Elizabeth class will not be fully written until it inevitably faces the crucible of modern peer-to-peer combat, perhaps in the contested waters of the South China Sea or the freezing expanses of the North Atlantic. It is a ship born of deep contradictions, built by a nation nostalgic for its imperial naval past, but constrained by the economic realities of the 21st century. It sacrifices the absolute maximum sortie generation and heavy airborne early warning aircraft of an American carrier in exchange for unprecedented automation, massively reduced logistical footprints, and a clever reliance on aerodynamic physics, instead of brutal mechanical catapults. The dual islands, the ski jump, and the electric drive are not second-rate compromises. They are highly calculated, brilliantly executed solutions to the specific strategic problems faced by the Royal Navy. It proves that in modern naval warfare, overwhelming your enemy with a checkbook is not the only path to dominance. Sometimes, careful, clever engineering can build a machine that fights far above its weight class. If you found this analysis useful, a like helps more people discover these deep dives. Thanks for watching.